like this. They should oscillate with a certain period, but not that sharp. Give me functions that are quite smooth, or others which make steps and jumps and so on. This you can do using a Gaussian process. And here, it's just the formal definition of a Gaussian process here. It has now not one single mean, but a mean function, and it has a covariance function. And this covariance function is actually defined over all the range of the possible x here. So this is no longer actually a vector or here a matrix, but in principle this itself is a function, and the function we can also represent as an infinitely dimensional vector. It's the limit of it. And this would be an infinite dimensional matrix. And you see here two pictures. This is just random sampling from a given distribution. We will see they come from the kernel. This is also called a kernel function, this k. That's why k is used. And after using actually Bayes' theorem to calculate the posterior distribution and to make predictions, actually I fix it to the measured values. And you get an uncertainty in between that you say, what had you sampled a point in between? I could say, most probably it would be here. But I can also give you at each point a certain uncertainty that this point would be there. Of course, the critical thing using Bayes' thinking is, how do you define a prior? And this is also the biggest criticism to all Bayesians. How do you choose the prior? Because there you actually define what you want to see a little bit. And sometimes you resolve by this that your first prior is just flat. Then you're safe off. Then you say, okay, let the data talk, but my first prior is just a flat distribution. I don't say anything about it. It could be anything. But then you do iteratively these predicting steps, take new data, and suddenly actually the distribution of the priors will come out automatically. Okay, a Gaussian process are extensions of multivariate Gaussians to infinite-sized collections of real-valued values. And yeah, it's kind of a distribution over random functions, like drawing out of a pot some random numbers. You just take now random functions. But you can define by giving your prior, and here mainly by defining this covariance function, how this function should look like. And using then the data to calculate the posterior or the predictive distribution, you can fix those points to the points where you have a certainty that the values must be like this here. You can fix it there. Okay. And yeah, probably just to the definition, what is a stochastic process? It's just a vector of random variables. And here this stochastic process actually has infinitely many random variables put together, and we can interpret it as a function. And then, if we take these infinitely many random variables and just take a finite set, then for a Gaussian process, this finite set will have a multivariate distribution. That's how a Gaussian process is defined. So we have infinitely many random variables. We take a finite set, and then if you look at the distribution of this finite set, of any set of these infinitely many random variables, it will have a multivariate Gaussian distribution. That's all we actually put in. And we normally write it like that. Then we say, okay, this function h, like our hypothesis, is drawn from a Gaussian process, which looks like a normal distribution, a Gaussian normal distribution, with kind of a mean vector, and here it turns out to be a mean function, and a kernel matrix or a covariance matrix. And at the beginning it's quite abstract. You will see how this works. Okay. Normally the mean value is not that relevant, so it's often set just to 0. We sample around 0, and here I've just given one example of such a kernel function. And the kernel function is called the squared exponential function. So it's just the distance squared, and it looks itself like a Gaussian distribution. You have to assume now this is now how only the covariance matrix of the Gaussian process is defined. It's again Gaussian. Gaussian and the covariance matrix is Gaussian. Means just that if two sample points are far away, they're not that highly correlated anymore. And the correlation coefficient goes down like a Gaussian distribution. So points that are far away means they're not that highly correlated, but points that are nearby, they're highly correlated. If I put in such a Kondo function as a covariance function, I will get kind of smooth functions because of this continuity. The closer x and x prime are, the more correlated they are. They must be close. And that's why actually out of this definition of the kernel function, it will result that we have smooth functions. That's nice. And we would say, okay, we sample now a function, infinitely dimensional, we sample a function out of this normal distribution given by the covariance matrix set sigma, and sigma is just evaluated for every data point that I have. Here I put in the data points, x1, x2, x1, x3, x1, x4, x1, x2. And if I had 1,000 points, this would be a 1,000 times 1,000 matrix. But it's not a problem to calculate. And we just do it. You see, that's the element ij of this covariance matrix. We put in here just the data points itself. And the kernel, we'll see, can be any function that's how do you say, that obey the laws of a kernel. So there are certain properties here for a kernel. Okay, and I've just stripped it down to the minimum what it is. And normally this is 5 sides of code, but here everything is inside. And it's explicitly programmed. So what we need is actually the distance matrix. The distance matrix is quite practical. What does it do? Yeah, in many topological problems you have actually, you want to calculate the traveling salesman problem, which is the shortest way to visit all those things. You have to calculate all pairwise distances. x1 to x2, x1 to x3, x1 to x5, anything. And this is already implemented here by this distance matrix, dm now. I take 100 sample points, and this now is the power of 2. Power means the exponent of this function. And what I change now is this here. This is the power, the exponent of this square law up there. And now you see what happens. We sample now an x in the range of -5 to 1, 100 points. And then we calculate the distance matrix of all these points. Here they sampled linearly, so evenly spaced. This is not necessary. We can sample in any order. We put the mean to 0. We calculate the distance matrix. Now I calculate this covariance function, covariance matrix itself. It's a 100 times 100 dimensional matrix. And without giving now any only the exponents, so distance squared, exponential minus a half times distance squared. This is a 100 times 100 function. And for nearby points, these values are big in the matrix. For faraway points, which have big distance inside, this will be very low. Now, I put this in a multivariate random distribution. Here. 100 times 100 matrix, and say, give me 5 functions. Give me 5 functions. Now functions means represented by 100 samples of this multivariate distribution, which we look now as functions. And then we plot it. And if I put in the power equals c, you see, quite nice functions. They look like spaghetti. They're quite smooth. But what shall I do with them? If I look at the distribution of those, they're Gaussian distributed. The most things are in the middle. And I could bend now and tune them as I want. They're just now random samples, but putting in now real data or calculating the posterior or the predictive distribution, you will see that they shrink to these data points and calculate at the same time actually the uncertainty of non-measured points. Interesting is if I change the power to 1, you will get these kind of functions. The same thing, just change power to 1. And now we get something like an index of a Aktienkurs. Could be actually And if I make it even more extreme, it looks quite noisy now. It's like a kind of a random walk process that we model now. So by just tuning one parameter, this exponent, you can sample from quite different functions. And what we do with those, we look after the break, because just sampling is nice, but what do I do with that? Okay, they represent a process that I know as prior, actually. And I know, for example, that a shareholder value looks like that. So I take probability functions like that. And I fit it to the curves that I have, to the data points I have, to get the best, most prediction. And the uncertainty to be able to predict, okay, how much do I lose if I invest in that? Or how much money do I make? And that's why. So our prior know-how can now shape these functions. We can select kind of appropriate functions, just defining these kernel functions. And how we will do that, we'll look after the break. Okay.